Hello, everyone, and welcome to Virtual Planetarium, Exploring Space, part of our MOS at Home programming. My name is Janine, my pronouns are she and her, and I'll be your moderator today. That means I'll be reading some of your questions and responses, which you can submit below using the Q&A button here at the bottom of your screen in the Zoom meeting. If you'd like to see captions during today's program, you can click on the closed captions button at the bottom of your screen and select show subtitles. And if you're joining us on Facebook or YouTube, hello! We're so excited to have you here today, but unfortunately, I'm unable to see your comments at this time. We're so delighted to have all of you here today as our audience. Let's meet our guide for today's journey.
Thanks, Janine. Hi, everybody. My name is Katie. My pronouns are she and her, and I'm going to be your guide today as we talk about physics, so special relativity. I will also be providing visuals throughout the program. We're going to kind of jump around from a few different things and play a game, a video game together, kind of. Not quite, but we'll show that soon. So as I mentioned, today we're going to be talking about special relativity. Earlier this month, this has kind of been our space math month. So this is the last Tuesday of this theme. But earlier in the month, we talked about gravity. There was an episode or program dedicated to gravity, and we talked about general relativity. So Einstein has kind of this whole theory of relativity that's split into two. We have general relativity and special relativity. So we covered a bit of that. And so just as a review, general relativity is basically connecting gravity to space-time, the fabric of space-time. So general relativity says that anything that has mass is affecting or warping the fabric of space-time around it. So in this picture here, you can see the Earth, which is very massive, and it's actually creating a curvature or like a well in the area around it that is curving space-time, and this is kind of how gravity works. It's the modern accepted interpretation that has a lot of evidence to back it up. And so this is the modern interpretation of gravity as opposed to kind of Newton's theory of gravity and Newton's laws of motion. Which are still relevant, but just when you get to the extreme, we have to bring in Einstein physics. And so that brings us to special relativity. Special relativity it kind of defines the relationship between space and time for objects that are moving at a constant speed. So we said that, the Earth is warping the fabric of space-time around it. Well, what is the fabric of space-time? What is space-time? We generally think of those two things, space and time, as two separate concepts or things, I guess. But through special relativity, Einstein proved that they are actually very closely related and they are relative. So it depends on who is doing the observing from where. All right, so I'm going to switch us now to just look at the two postulates of special relativity. So for special relativity to be true, you have to assume two things: that the laws of physics are the same in all inertial reference frames. So basically what that means, I'll break it down a little bit. A reference frame is essentially a point of view. So you could have someone standing on a train that's moving, and they would have their frame of reference, and then you could have somebody on the platform watching the train go by, and that would be another frame of reference. So in any frame of reference that is moving, or that has a velocity but is not accelerating. So it's maintaining the same velocity. The velocity could be zero in terms of somebody just standing, or it could be close to the speed of light. Just as long as it doesn't change, there's no acceleration happening there. And then the second thing you have to assume is that the speed of light in a vacuum is the same for all observers, no matter what reference frame you're looking in. And this is true, and this has been proven to be true. So the speed of light is constant. All right, so now let's go into space for a moment because I want to talk a little bit more about reference frames. And by the way, if you do have any questions throughout this program, I know that the content is a little bit different from what we usually do when we just kind of talk about objects in space. So please feel free to ask questions. If I'm not clear on anything, please feel free to throw it into the chat. I would be happy to take questions at any point during the program. So Janine, if you want to interrupt me at any point, please feel free to do so.
Sounds good.
Awesome. So let's talk about frames of reference. I mentioned the train example where you have somebody's perspective from on the train that's moving in one direction. Also, you have somebody that is maybe on the platform that's not moving, that's observing the train go by. It can also be argued that even though the train is the one that's doing the moving compared to the person on the platform, the opposite could be true. The person on the train might not know that they're moving, and it looks like the environment and the platform around them is actually zooming in the opposite direction. So that's kind of really the core of special relativity, is that everything is moving in some way or another, and it's all relative to one another. So you could say that I'm sitting in this chair, I'm not moving at all, but technically the Earth is spinning, right? The Earth is moving around the sun. Other objects are moving in relation to me, so I might look like I'm moving compared to that. It's all relative, and so is time. Okay. So I want to just give you one example of this kind of weird relative motion that I'm talking about by talking about retrograde motion. So retrograde motion in the solar system happens when the Earth, we can see it really well when the Earth is passing one of the outer planets. So as you get farther and farther away from the sun in the solar system, it takes a longer time to orbit around the sun. So those planets are moving slower the farther out you go. So Earth is moving faster than Mars, Jupiter, Saturn, Uranus, Neptune, anything in the Kuiper Belt, any of those objects, it's moving faster than. And so when Earth passes one of these objects, we end up seeing in the nighttime sky like that object is actually moving in the opposite direction. So if I fast forward time a little bit, and we can use Earth and maybe Jupiter as an example. So if we fast forward time, and hopefully I can get it to a good point so we're not going too fast. There we go. And so you can imagine as the Earth is passing in front of Jupiter, imagine looking up at the sky from the perspective of the Earth. It would look like Jupiter is actually moving backward. It's kind of the same deal when you are on a train and maybe there's another train next to you and you're looking out the window and it feels like you're moving even though it's really the other train that's moving. It's the same kind of thing. Everything is relative. All right, so now I want to actually get a little bit closer to the Earth, and we're going to start talking about what happens when special relativity, the effects of special relativity start to become obvious. So in everyday life, nothing is actually moving close to the speed of light. Speed of light is the speed limit of the universe. It's the fastest thing in the whole universe, and nothing that we do here on Earth is even remotely close to that speed. But in order to feel the effects of the speed of light, or excuse me, of special relativity, something needs to be moving close to the speed of light for anything weird to happen. So let's take the example of astronauts on the International Space Station. So let me put up some spacecraft and see if we can find the ISS around here. Maybe not. Maybe it's not in this data set, which is okay. Okay, that's all right. Okay, so actually one more thing before I want to give this example of the astronauts on the ISS, just to kind of help clarify what the concepts we're going to be talking about are. if you are on a moving train and you shined a flashlight, then the person that's standing on the platform, you would think, would measure that beam of light as going the speed of light plus whatever speed the train is moving at. And the person on the train would just measure it as the speed of light. But this is not the case. The speed of light, no matter which reference frame you're looking in, is always constant. It's always the same. And if you can think back to physics or math class long, long ago, you can think back to the equation that distance over time equals velocity. And if we see that the speed of light is constant no matter what, that means that in that scenario of a train moving really fast with a flashlight beaming out, that means that the distance or the time has to change in order for the velocity to stay the same of the speed of light, which we know it is. It's always constant. So when the time changes, this is a phenomenon called time dilation. And when the length of something changes, that is called length contraction. And so from the person on the platform observing this happening, this train that's maybe moving close to the speed of light, some weird things start to happen. So we can use the example of these two astronauts. They are twins. This particular experiment was conducted by NASA. It was called A Year in Space. And both of these brothers, they share the same DNA because they are twins. And so one of them stayed on the surface of the Earth while the other one went up to the International Space Station to spend a year in orbit around the Earth. And so the main purpose of this was to see how long-term effects of microgravity and just being in space would affect the body. So eventually we can send people into space for long periods of time, potentially, back to the moon, potentially to Mars. So this was kind of the main goal. But the effects of special relativity were also at play here because the International Space Station moves at 17,000 miles an hour around the Earth. So it does one orbit of the Earth every 90 minutes, which is incredibly fast. It's nowhere near the speed of light, but it's much faster than anything we're used to on the surface of the Earth. And so after spending a year up there, the effects of relativity actually did make a little bit of a difference. So when Scott Kelly, the astronaut on the right, came back to the Earth, he was actually just a few milliseconds younger than his brother Mark. Because the closer you get to the speed of light, the slower time passes for an outside observer, which I know sounds super weird, but I'm going to show you exactly what this looks like in a game in just a moment. There are also some weird things that can happen due to objects that have very strong gravity. So not necessarily like the Earth, although the Earth certainly can have an effect. But basically what happens is as an object is spinning in the fabric of space-time, it can kind of twist it all up. And then you can measure the effects of that as well. So there is time dilation due to things moving really, really, really fast, close to the speed of light. And then there's also time dilation due to gravity, but we're not really going to talk about that today. All right, so that's a little bit of what happens to time as something is sped up. But then we also have distance being affected as well. So from an outside observer looking at something that's moving at the speed of light or close to the speed of light, they would measure that object as being shorter than someone would measure the same object in the same reference frame. So we see a difference in length as well. But now let's go ahead and switch to the game. So I can actually show you what is going on and explain it hopefully a little bit clearer. But first, I'm going to pause and see if anybody has any questions so far.
Don't see any questions, but if you have them, post them in the Q&A and I will ask Katie.
Perfect. All right, thank you. So what we're going to be looking at is a game that is called A Slower Speed of Light. And this particular game was developed by the MIT Game Lab. And the intention was to simulate what it would look like, what your surroundings would look like if you could move at the speed of light or close to the speed of light. And the way that they kind of, built this in was that you could actually lower the speed of light to something that, is familiar, like walking speed. So that's kind of the concept of the game. And you'll notice a few different things happening. So the way that the game works is that you have to, let me start playing it here. There's a little bit of backstory right at the beginning that kind of sets everything up. But basically, you're a spirit that is in this environment, in the spirit world, that can slow the speed of light by picking up these orbs. So once you get to all 100 of these orbs, once you collect all of them, then you would be moving at the speed of light. And so your environment around you starts to look really weird. And depending on how fast you're going, you start to notice different effects happening in, your surroundings. So the first thing that you start to notice, and I was going to play this live with all of you, but then I realized that nobody wants to, sit down and watch me struggle to collect all of these orbs together. So I can actually scrub through parts of this video. So each of these orbs is slowing down the speed of light. And you'll notice at the bottom there that you can see the visible part of the spectrum. You've got infrared, which is over on the left, and the ultraviolet, which is all the way on the right. Once you start speeding up to a significant fraction of the speed of light, more of the electromagnetic spectrum is actually visible with, theoretically, it would be visible. More of it, more colors would be included in the electromagnetic spectrum. That would be part of the visible part. So you can see that it's widening with every extra ball here that we're getting, every orb. So we're seeing more of the spectrum. And if we kind of scrub through a little bit more, you'll start to see that the colors are changing. So this is called the Doppler effect. So if you're moving very fast in one direction, everything would start to appear blue or violet because the wavelengths of light that is really kind of the shorter end of the spectrum here, the wavelengths that have more energy, higher frequency, shorter wavelengths start to everything kind of starts to condense. Light starts to condense and enters this part of the spectrum. So things appear blue. And if you were to go backward and move away, things would start to shift toward the red part of the spectrum because wavelengths would get stretched out. So whenever you see in this game that we're going forward and you see it turn blue for a second, that is the Doppler effect. You're experiencing the Doppler effect. And as we keep kind of collecting orbs, we're at 70 now, you'll notice that there are just different bands of different parts of the electromagnetic spectrum. Objects appear brighter in front of you because you're moving toward them so that you're hitting more light. So that is another kind of apparent feature of special relativity and moving at the speed of light. And we can get even a little bit further into the game here. And if anybody's sensitive to lights or kind of drastic changes in lighting or anything like that, I will just put that warning out there because it gets a little bit flashy in just a moment. We'll fast forward even more to about here. And as we move faster, you can actually see some of the time or the length contraction happening. So things start to warp in their sizes. And we can go a little bit farther. So this is after all of the orbs have been collected, and now you can really see the effects of time or length contraction happening here. As you get faster, things get smaller, they shrink, they start to curve and bend as you pass by. Time is also changing, but it's a little bit hard to portray that aspect in this game. And so this is just a really cool, fun, easy, free way to kind of experience the effects of special relativity. Now, what was really cool is the museum had a partnership with the MIT Game Lab a few years ago, and they collaborated to make a version of this game that used the Museum of Science. So we can also look at this version, where we see these ducks passing by. This is all normal. And then they start to move much faster, not quite at the speed of light, but a little bit, under half. And you see the Doppler shift happening there. Once again, the blues and violets, the wavelengths are squishing. All the wavelengths in front of you are squishing, so they appear bluer. And as we move away, the wavelengths are stretching out, so they appear redder. And now if you were to move at the same speed as the boat, so if this boat's moving at a fraction of the speed of light, but you are as well, it will appear normal because you're in the same frame of reference. So now you can start to see some of the ultraviolet and infrared and other wavelengths of light that are not normally visible to the naked eye, but they would become visible once moving at a fraction of the speed of light. All right, and that one is done. There were two versions of that one, but I got the shorter one so that it has captions. So I will pause there and see if anybody has any questions. I know that there is a lot of information and I'm still learning as well and trying to figure out the best way to communicate all of this, but it's a very weird world and physics is super weird.
I have a so we do have a question about what the game was called, and I will go ahead and post that in the chat so you guys can see the link, and I'll also have it at the end.
Awesome.
But Katie, I have a question, which is, I've heard of things like Einstein crosses. Are those effects of special relativity or are those general relativity?
That's a good question. I actually don't know what Einstein crosses are. Do you have an idea of?
Yes, so it's like you have a really massive object like a black hole or a galaxy or something, and there's an object that's behind it, and we can see the light of the object behind it, and it appears kind of above, below, to the left, and to the right, so you get four images of the same thing.
Yeah, so that is called gravitational lensing. So the light of an object behind a very massive object like a galaxy or something like that is actually bends as it moves around this really massive object. And so that bending makes it look like there are four different images of that object. And so you're actually able to see something behind a very massive, a galaxy that's in the way, for example. So general relativity is certainly at play there, right? Because that really massive object is causing a very deep gravitational well. It is curving the fabric of space-time quite a bit. And I'm sure that there are effects of special relativity going on there as well.
Okay, and then I have another question. You talked about the Doppler effect. And I was wondering, like, what observations do astronomers make that, like, they learn from the Doppler effect, this red and blue of things?
Yeah, that's a great question. So, astronomers can use the Doppler effect to figure out what direction things are moving in. So, let's see if we can. I don't think we can see other galaxies in this particular program, but if you were observing another star and you looked at its spectrum, so its light signature, and you saw that it was all shifted a little bit toward the blue end of the spectrum, or maybe toward the red end of the spectrum, you could tell if that star is moving toward you or away from you. Because if it's moving toward you, again, those wavelengths of light are kind of like squishing together. So they get, the wavelengths become shorter, and so they appear blue. And if it's moving away, they kind of stretch out and appear redder. So that's how astronomers tell which direction stars are moving in. Also, other galaxies. So galaxies can be shifted in their spectra as well. And ultimately, you can tell that the universe is expanding partially from this red shifting, which is a little bit different than the Doppler effect, but it's kind of the same concept.
That's really cool. How do astronomers know that like those aren't the original colors they're supposed to be? How do they know that they're bluer or redder than they should be?
Yeah, so when you look at the spectrum of an object, it might show the signatures of hydrogen or helium or, whatever elements it's made up of. But stars tend to be made up of similar material. Certain stars have more metals than others, but for the most part, astronomers know what signatures should show up. And so if they have all of those signatures, but they're just kind of offset a little bit, then you can kind of tell that it's, either moving away or toward, depending on which way they're offset.
So the pattern is like all the same, it's just not in the right place.
Yeah.
Cool. I think that's all we have time for today. So I guess I'll let you say goodbye.
Thank you. Thanks, Janine. Thank you, everyone.
Yes, thank you all so much for joining us today. We hope you had fun. I hope you learned something. Maybe we stumped you a little bit, and that was maybe fun for you. If you would like to see other virtual programs that we offer specifically about space or maybe about animals or climate change or something like that, you can check out what's happening on our social media channels by following us on Facebook or Instagram. You can also check out www.mos.org/mosathome. If you enjoyed today's presentation and would like to support more programming like this, please visit engage.mos.org/welcome to support MOS at home. And thank you to everyone who has. Today's program was produced using this free software, NASA's EYES. That was the one with all of the orbits of the planets. And also, Katie mentioned the special relativity game. So again, it's at the bottom. It's called The Slower Speed of Light, and you can find it at gamelab.mit.edu/game/a-slower-speed-of-light. Thank you all for participating today, and we hope we'll see you again soon. Bye.